Hello there, and welcome to Math. My name is Xander, and today we're going to be looking at non-Euclidean geometry. Now, what exactly is non-Euclidean geometry? Well, non-Euclidean geometry is any type of geometry in which the parallel postulate is not true. Okay? Whoa, not okay. Hold on. What the heck does this even mean? Euclidean postulate? What are these words and how do they relate to any form of geometry? I sure as heck didn't learn about this when I took geometry. Well, not to worry. Let's go ahead and dive in to see what this statement even means. We'll go right into what this first weird word is, Euclidean. What does that relate to? Well, it actually goes back to the very origin of non-Euclidean geometry, which goes back to this man named Euclid and his elements. So Euclid was a Greek mathematician, also known as Euclid of Alexandria, or the father of geometry. He kind of laid the foundation for modern-day geometry itself. About 300 BCE, he published his Elements, which is a collection of 13 books, kind of holding all of his discoveries of mathematics. But today we're mainly going to be talking about his discoveries in plane geometry. That's plane geometry as in geometry on a plane surface, on a planar field. So in his Elements, he kind of lays down 5 things called postulates, which are sort of rules that describe this field that he's working in. And these 5 postulates perfectly describe planar geometry, or Euclidean geometry, as we're going to call it. So these 5 postulates, they're going to sound a bit weird when I read them off, but they're actually quite simple and they're quite easy to grasp. So the first one states that a line segment can be drawn joining any 2 points. Essentially what this means is that we have 2 points and there's a line that connects it. The second postulate states that any line segment can be extended indefinitely in a line, which kind of takes the idea of the first postulate and says that this line segment can be extended forever in both directions. The third postulate states that given any line segment, a circle can be drawn having the segment as the radius and one point as the center. So this essentially means that we can take a line segment, which is the radius, and one endpoint as the center, and draw a perfect circle using just those pieces of information. The fourth postulate simply states all right angles are congruent. And that's just how it sounds right here. Now, Euclid's fifth postulate is probably the most controversial, in that Euclid was never able to actually prove this. This fifth postulate is also known as the parallel postulate, and is stated as follows. If 2 lines are drawn which intersect a third in such a way that the sum of the inner angles on one side is less than 2 right angles, then the 2 lines inevitably must intersect each other on that side, if extended far enough. Now, that is a very complicated way of basically just describing how parallel lines work. An easier way to describe it is just saying this. Given a line and a point, there can only be one line that can be drawn through this point in which these 2 lines never cross. Many later geometers questioned this parallel postulate, which gave rise to many new geometries. And the question was raised, what would a geometry look like if the parallel postulate or any of the other postulates were false? So this gave way to a mathematician called Nikolai Lobachevsky. And to seek an answer to this question, he looked to the sun, to the moon, and the very planet on which he stood on, and which all those objects are spherical. So this kind of set the basis for his works in geometry. In 1829, Lobachevsky published his On the Principles of Geometry, in which he perfectly explains a consistent geometry in which the parallel postulate is false. So, with Earth as his basis, Lobachevsky came to the point that the parallel postulate holds on 2-dimensional planar geometry, but not in the 3rd dimension. This was the basis for establishing non-Euclidean geometries. Later, in 1854, German mathematician Bernhard Riemann concluded that different non-Euclidean geometries are possible based on a given number of dimensions. We'll talk about this in a bit. First, let's talk about what Lobachevsky was describing when he was talking about the Earth, something called spherical or elliptic geometry. So in Euclidean geometry, the shortest distance between 2 points is a line, and it's straight. But in non-Euclidean geometry, the concept corresponding to a line is a curve called a geodesic. It is the shortest path between 2 points on a non-Euclidean plane. You can see that here on this on the sphere here. We have 2 points, and the shortest distance to them proves to be a curve shape. Now, if we extend this geodesic to go all around the sphere, while keeping the same radius and center as the sphere, we'll get something called the great circle. A great circle is what we use to show geodesics on a sphere, like the equator on a globe or the lines of longitude. They go all around the Earth while having the same radius and center of it. Now, this point here directly proves that Euclid's parallel postulate does not work on a sphere. We can see that given 2 or more geodesics or great circles revolving around a sphere, will always touch each other no matter what. These geodesics converge. Another way to show this is pictured right here. This image depicts Euclidean geometry, in which we have several lines perpendicular to a third. These lines will always be parallel to each other, thus they'll never touch, proving Euclid's parallel postulate correct. But if we take this same design and put it on a sphere, we see that these lines will always converge towards each other. Thus the parallel postulate is false. We take another example of a triangle on a sphere. Here we have a triangle. I don't know if you can see it, but each of these angles on a triangle is 90 degrees. On regular Euclidean geometry, this is not possible, as the angles of a triangle can only add up to 180 degrees. As on a sphere, they will always be more than 180 degrees. The next type of geometry, called hyperbolic geometry, shows to be the opposite of spherical geometry. If spheres have positive curvature, then the hyperboloid would have a negative curvature. And we can see the same design put on a hyperbolic plane, which can be imagined to look sort of like a saddle shape. Now these geodesics are divergent and will get further apart from each other, as if space were being stretched between the lines. As for triangles on a hyperbolic plane, here we can see that the angles will always add up to less than 180 degrees. This type of geometry was what Riemann was talking about when he claimed that there could have been numerous non-Euclidean geometries possible given a certain number of dimensions. This is only one example. As we multiply the amount of dimensions, the laws of the non-Euclidean can expand further and further. However, the hyperbolic and elliptical types of geometry are the main two associated with non-Euclidean geometries. So from here, we'll go to some practical applications. Now, Riemann once said that the value of non-Euclidean geometry lies in its ability to liberate us from preconceived ideas in preparation for the time when exploration of physical laws might demand some geometry other than the Euclidean. Now, this time that he speaks of, this future in which we need to use non-Euclidean geometry in our life, is today. And one of the main examples of this existing in modern day is actually air travel, which unfortunately we can't really do right now. Nonetheless, it's still important to understand. The Earth is in fact a non-Euclidean plane, so we have to account for this in flight. Now, if we wanted to, say, travel from San Francisco here on the west coast of the United States all the way over to maybe Paris, in Euclidean geometry, this would state that the shortest distance between these 2 points would be a straight line. But since this is a spherical geometry and it's non-Euclidean, we have to account for its geodesic, in that the shortest distance between these 2 points actually makes a curved shape. So airplanes, when traveling for this, would make an arc when traveling due distance. Taking a more scientific approach to the application of non-Euclidean geometries, it actually comes up in one of the most important theories about our universe to this day. That is the general theory of relativity. Einstein once said, "To this interpretation of geometry, I attach great importance, for should I have not been acquainted with it, I never would have been able to develop the theory of relativity." So in Einstein's theory of general relativity, he actually describes space-time as a non-Euclidean geometry, in which it actually warps and curves near gravitating bodies like the sun and planets. A good way to imagine this is if we take, say, like a rubber sheet and drop a bowling ball in it, it would sink. It would sink into this field right here. And if we take like a marble and put it on the side of this curve and give it a little push, it'll actually roll around the bowling ball, symbolizing a planet orbiting a sun. Now, this wouldn't be possible in the sense of Euclidean geometry, as that says it can only go in a straight line. Now, if we're talking non-Euclidean, this shows perfectly what's happening. Now, to conclude, let's go back to the statement I presented at the beginning of this presentation. Non-Euclidean geometry is any type of geometry in which the parallel postulate is not true. We now know the origins of Euclid and his planar geometry, as well as his 5 postulates, including the parallel postulate stated here. This gave way to the possible ideas of a non-Euclidean geometry in which this parallel postulate did not hold to be true. Now we are living in a world where this type of geometry is essential to the way we do things and how we think in our daily lives and in science. Thank you guys very much for watching, and thank you, Mr. Radliff, for being an epic teacher throughout the years. Here are my sources for my project, and I hope you have a fantastic day.